Good afternoon, everyone who's joining us here in person, and also to everyone who is joining us online this afternoon. We have our next presentation in the research seminar series, which is being presented by Dr. Mariana Barnes. As we begin, I'd just like to pay our respects to the traditional elders, the Larrakia people here in Darwin, and also the Aranda people down in Alice Springs or Mpantwa, just in case anyone's joining us online as well. I'd also like to pay my respects to the traditional owners of that country too, and also extend our respects to anyone who's joining us, Aboriginal and Torres Strait Islander, here in person or online, and our respects to elders past, present and emerging. I will hand over to Dr. Mariana Barnes, who will have some time at the end for questions, and we'll go to questions in the room first before we go to questions online. Thanks so much, everyone.
Thanks. Welcome everyone to today's seminar, and as she just beautifully said, I also would like to acknowledge that we are meeting on the Larrakia land, and I pay my respect to elders both past and present. So I'm Mariana, and today I would like to talk to you about how you can let the HPC aid you. So I'll be talking about Menzies and CDU's high performance computer. So let's start with the basics. What exactly is high performance computing? Really, it's a cluster of powerful parallel working processes. If you imagine it in a way, it's basically like several computers just connected to each other, sharing and parallel working the workload. And it consists out of three main components. You've got the computing nodes that actually do the work, you've got the storage, and obviously the network that connects everything. So you as a user, once you log in from anywhere, you will end up on the login node, and then you will send your job off that will then go onto the compute nodes to work its magic. Just to give you an idea what kind of performance we are talking about here, the world's most powerful supercomputer Frontier does 1,100 petaflops per second. So that's a computational unit on how they measure supercomputing. But basically that's 1 quintillion operations per second. That's really a hard number to fathom, but our Milky Way galaxy is 1 quintillion kilometers wide. So that's how many operations the supercomputer can do. That's crazy. Maybe also interesting for you is Terralia's most powerful supercomputer, called Cetonix, after the Quokka, is only 27 petaflops in comparison to that. And Apple has just released the newest M2 Pros. They're sitting at around 0.015, so quite a big difference. So why do we need high performance computing? So for Menzies and for CDU, this helps us to stay competitive, to be able to do this sort of data analysis. Talking about data analysis, the main point is that we are working, and even more now, with multidimensional data sets, what we call big data. One little example here, our PhD student, Anto, he's recently analyzed around 250 Vivex isolates, and he started with 0.7 terabytes of data. And because of how these sort of data analysis work, you create a lot of really big temporary files in between. So we actually ended up with over 5 terabytes of data just from doing one analysis. I can't even put that on my laptop. I only have 500 gigs of storage, so I assume it's probably very similar for you guys. As you can imagine, this sort of data sets needs computational power. And if you have that computational power, this can save you a lot of time. And time is money, so it also saves you a lot of money. And at this point, I can also say this system is free for all to use. And it's been recently also released to students. So if you are a student, honors, or whatever it is you're doing and you're interested, you can also use this cool resource. I'd like to take a moment to just say goodbye to Cheetah. So as you might or might not know, Cheetah is Menzies and CDU's previous high performance computer, and it came to life in 2014. I'd like to say because of Phil's persistence and passion in supercomputing. That's him in front of the old system. And it's literally been turned off just last month. So that's it, no more Cheetah, that's it. Instead, the new system went online live in May last year. So it's not even really a year old yet. And we named her Ada. Why did we do that? Well, the system was named just on International Women's Day. And she was named after Ada Lovelace, who you can see here. So Ada is an English mathematician and writer, and she's basically regarded as the first computer programmer. That's because she has designed this wonderful algorithm that you can see here that was supposed to be used on Charles Babbage's analytical machine that he proposed in 1840s. So 1840, the analytical engine is kind of like a theoretical first computer. It never came to be, but she designed this algorithm to be run on that theoretical machine. So I think that's a really fitting name. That's her there, and that's how she looks when you open one of the storage racks up. Not as impressive as the really big supercomputing centers, but still great. She's got 8 computing nodes, and each of these nodes has 32 dual-core CPUs. For those tech geeks of you, these are AMD cores, not Intel. And as a comparison back to my Apple laptop, the Apple laptop, the new generation, sits at around 10 to 12 CPUs. So even one of these computing nodes is a lot more powerful than your average laptop. We also, and this is new, now have a GPU node with 232 GPUs from NVIDIA. The old system didn't have any GPU power, so this was basically a new trial on how good this is going to be for the users. We also have 224 terabytes just of raw storage, and one thing, it does run Linux. So for those of you that don't know, Linux is an operating system just like Mac OS or Windows, and it is just the main dominating operating system that's used in high-performance computing. However, it doesn't have a graphical interface. So most of you are probably used to point and clicking your way through your computer. This is literally what you see when you get onto the system. So you're just on the command line. And I know that might intimidate a lot of you, but let me tell you, it's easy to learn. And once you do it, you might actually never want to go back. Ada is managed by ITMS that deal with all hardware and licensed specialty software kind of things. And it's managed by Menzies that generally is software and user management, Menzies being me, and ITMS being my lovely counterpart, Corey. And also you can now log a job with Logit if you request access, if you want some specialty software, or if you want to do some training. I'd like to give you a couple of examples, just exactly what you can do on the HPC. So first of all, we've got at the moment 44 users across Menzies and CDU, as well as external collaborators. And it actually reaches far beyond Australia. Like we've got collaborators using it from America. We've got collaborators in Indonesia, in Ethiopia, and in Vietnam. And that's just the countries I know of. We also have a really wide variety of applications. For CDU, for example, they mostly do modeling. Here at Menzies, we mostly do genomical analysis, but we've also had a student do statistics on it last year on Stata. What you can see here is the utilization over the CPUs and here over the GPU. The reason I included that, other than it's a pretty picture, is that our system currently isn't at full capacity yet. Why is that great? If you've ever tried to get research capacity on one of the national research centers, you would know that generally you'll have to put an application in for resources. You'll wait for that application to go through, if it does. And once it does, you'll wait for your actual resources to be allocated. Once you get them, you will then run your job. And if there's anything else you got to do, you will have to start the whole process again. This system is local, it's here. You don't need to move any data over. You've got your data straight there. And when you want to use it, generally you can use it straight away. You don't have to wait for anything. You run your job. If something failed, you just run it again. You can trial and error yourself through whatever you're doing, which I think is an amazing advantage and saves you time again. The only maybe exemption from that is the GPU node. As I said, this is new. So the GPU, we didn't have any experience with it beforehand, but it turns out it's quite liked. So it's actually quite busy. Having said that, I've been doing some stuff on the GPU node myself, and generally I didn't have to wait more than 1 or 2 days for my things to run, just to keep that in mind. Now, Robin was so lovely to share one of her projects with me that she'd run on the previous system. So I can show you just one example of what people did. And that was a microbiome analysis she done on 28 children with protracted bacterial bronchitis and 8 controls. So she took respiratory samples and she looked at the microbiota, bacterial biomass, and inflammatory markers. And she created this beautiful, it's called a hierarchical group average cluster analysis. Sorry, that's a mouthful. And what it shows you is that basically that PBB data falls into two specific groups. You've got one group that is dominated by a known respiratory pathogen, in this case with the orange bars, for example, Moraxella catharhalis. And the other group is actually showing a really diverse microbiome. So that was quite interesting finding. And now they're actually working on trying to find out if these specific profiles have a direct correlation with the clinical outcome. That's what they're currently working on. If you're interested, read the lovely paper from Robin. Another work that I am currently involved in doing is analyzing targeted amplicon sequencing data. We are currently developing a microhaplotype-based amplicon sequencing assay to determine P-Vivax relatedness. As you might know, malaria is caused by the parasite Plasmodium. There's 5 different species of Plasmodium, with Plasmodium falciparum and Plasmodium vivax being most prevalent. The kind of special thing about Vivax is that it tends to form dormant liver stages, and these dormant liver stages can reactivate and cause what we call a relapse. So when you have a P. vivax malaria reoccurrence, it can be either to this relapse, or it could also be due to recrudescence where the treatment failed, or it could be due to reinfection where you have a completely new infection of malaria. And to differentiate between these three is extremely difficult. And as of yet, there's no real consensus on how to do this analysis. However, there was a lovely paper by Amy Taylor that they created a time to event model to try to solve this question, but this time to event model needs genetic data. So we were interested in creating an assay that can quantify the relatedness between the paired P. vivax isolates using identity by descent. If you imagine it in this way, if you basically have a completely new infection, you would think that the genetic profile of that infection is possibly quite different to the first one. So they'd be strangers. They wouldn't be genetically the same. If you'd have a treatment failure, you would assume that they would be kind of the same because it's the same, the same sample basically that just didn't get cleared out. And if you have a relapse, we assume that they're going to be siblings. So they're genetically somewhat similar. And then also, it should give us enough information to actually do spatial temporal evaluation. We wanted it to cover most of the genome. We wanted it to be cost efficient and high throughput. And because there was another pretty good paper by Amy Taylor, she suggested that around about 100 markers, or what she calls microhaplotypes, would be the best number to do that. So what is a microhaplotype? A microhaplotype is a small genomic region, roughly around 200 base pairs. And the good thing about the microhaplotype is that it contains at least 3, but up to 10 biallelic SNPs in that region. So this is, for example, one microhaplotype here, and you've got 3 SNPs in there, and obviously you can have a wide variety of genotypes over that microhaplotype. If you then got 2 more microhaplotypes, then your final haplotype will actually consist out of a combination of all these different microhaplotypes. In collaboration with Sanger and AGRF, we then created a single Illumina RAMP-seq assay that had 146 of these candidate microhaplotypes. Why 146? Well, we basically combined 2 assays with 100 and had to take some out that they already knew wouldn't work, just to make sure that if some of these markers failed, we could replace it with a different one. We also incorporated 4 drug-resistant targets and 2 mitochondrial amplicons. So the mitochondrial amplicons are just used to do speciation in case we've got, for example, a mixed infection that could help us to find out what kind of Plasmodium we're looking at. And we tested this assay in 192 samples from 10 different countries. To give you an idea on what the analysis actually looks like, so when you first get your data back, you get a file that is somewhat like this. You will have an identifier at the top, then you will have a sequence, which we call a read, and then you will got the quality scores. So you really have a really large file just with this. So the first thing you do is you need to quality filter it to make sure you've got just good quality data. You trim primers off and all that jazz. And then you need to actually put these little snippets back to what kind of target you actually want to look at. So we call that an assembly. And once you've assembled that, it can look somewhat like this. What you can see here are actually 2 amplicons, 2 amplicon targets. They're slightly overlapping in this case. And something we look at there is what we call coverage, is just how much of that target, this one, for example, here is actually covered by our reads. If you have a full coverage of 1, you would have the full thing covered. If you, for example, had a coverage of 0.5, it would only be half of the target. And another thing we're interested in is generally to say just how many reads can we see over that target. We call that read depth. The reason we're interested in read depth is if you want to look at variations in the genome, you've got to make sure that your variation is actually there. So you want a depth, a certain amount of depth over that variation to make sure it's true and not a sequencing error. So we did that, and what you can see here from our first run is that most of the markers worked. Not all did. There's some here that obviously didn't sequence very well. And also looking at the coverage, if you have a low depth, you kind of would expect also to have a pretty crappy coverage. And yes, we do see that, but we also see some markers that had a pretty crappy coverage, although they had a good depth. And that's an indication for the target not being really fully sequenced, and with that, not really great for us. We also looked at if the assay was actually working in all the different countries that we included. The reason we do that is because we want our assay to be really globally applicable. Sometimes when you have these sort of targets and you have primers, then in certain regions you can have variations in the primer region, and then your target wouldn't work in that region. So we wanted to make sure all of our countries work, and they did. So that's great. We then went and made a decision tree, basically looking at, do we have enough depth? Do we have enough coverage? Are we still evenly dispersing over our genome? And from that decision tree, we ended up with a single Illumina RAMseq assay that had 94 assayable microhaplotypes, still the 4 drug-resistant markers, and 2 mitochondrial amplicons. And this is brand new data, so I'm happy to present to you that it worked. And we actually have all of our markers sequenced. I mean, there's one that looks pretty sad here, but it still has a depth of 120, so it worked. And if you look at the coverage, none of the markers actually fall under 0.8, so we're quite happy with that. So these are just 2 examples of something you can do. There's a lot more things that are, possible with the machine. There is a Wikipedia page and the CDU Confluence Wiki that you can look at that will give you information on how you use the system. There's training material on there, that will give you some information on how to use command line if you're new to this. And also there's a list of all currently installed software. Just one note, there is specialty software on the system, just as data that I've previously mentioned. That's licensed software, and generally we don't hold any HPC licenses. If you are interested in licensed software, you might have to purchase it for your group, but it's nothing, we can't do. Just have a chat to us. And really, this software list isn't set in stone, so it really is about what is it you need. So I hope that I've convinced you that this is a really great resource that's local, that's amazing, and really how this HPC can aid you depends on you. Feel free to gain access by just pressing this lovely little button on the Locket tile or sending me an email to mariana.barnes@menzies.edu.au. And if you have a project where you think that this might be valid for you or interesting for you, come and have a chat. I'm quite friendly. That's about it. If you have any questions, I'm happy to answer.